Good morning, class. Today we're going to be looking at section 9.2.1 in our textbook. The title of this section, actually, I don't know what the title is. I think it's inequalities with two variables. That's certainly what I'm going to be talking about. And we've definitely been looking at inequalities for a while, but every instance that we've looked at so far has just had a single variable. So, for example, maybe we've looked at 3x is greater than 15, or the absolute value of 2x minus 1 is less than or equal to 10. And we've, over the last week and yesterday, we've been looking at ways of figuring out values of x that make that true. And that's today what we're going to be doing. We're going to be finding values of two variables, x and y, that make a particular statement true. Now, when we looked at when we look at linear relationships or quadratic relationships, or when we look at exponential relationships, variable I'm sorry, values of x and y that make a statement true, right, lie on that particular curve. If we looked at a really simple curve like y is equal to negative 2x plus 3, we can see in this case that we clearly have both our variables here, right? We've got our x variable and we've got our y variable, and we also have our two parameters. Our parameters for a line are the slope parameter, and we can see that, and we also see our y-intercept parameter. So both of those are there, and you can see our y-intercept parameter right here at positive 3, and then our slope is down 2 units, and over a single unit, and we land back on it. Down 2 units and over a single unit, and we land on it. There are lots of xy points that satisfy this relationship. In fact, any xy point that is on this line, right, will satisfy this equation. What we want to do now is we want to consider, okay, so what if it's not the case that they're equal? Well, remember what solutions look like to this equation, right? Solutions to this equation turn out to be pairs of points in the form x, y, right? So solutions are points that lie on the line. So if I look at this, 3 comma 0 is a solution to this. I could look at this point 2, negative 1. It is a solution to this equation. That's an ordered pair that will make that statement true. It is indeed true that if I take in and I plug in 2 for x, I end up getting negative 2 times 2 for x plus 3, which is what? Negative 4 plus 3, which is negative 1. You can see when x is the number 2, when I plug in 2 for x, it makes this y value become negative 1. So that's an example. So what we're looking at is pairs of points that make a statement true. So if we were to consider, instead of the equation, if we considered this inequality, y is greater than the opposite of 2x plus 3. Well, first of all, because y is strictly greater than, all of a sudden we can't talk about points that live on this line, right? Points on this line are not going to be solutions, and we show that just by coming in, and I think I can grab a color ink. Well, I guess I'll just grab this color, this black, and I can just come along and I can say, whoops, that's white. I can come along and I can say, you know what, this point right here, I'm gonna try to make this a dash line. So I'm making it a dash line by taking away bits of the purple. So this dash line indicates that this is just a boundary line. Just like before with one variable inequalities, we had a boundary point. Now we've got a boundary line. And what we're looking at here are, we need to decide where our solutions live, right? And our solutions could be either the points that are above this curve, right? All these y values that are above the curve, or it could be the y values that are below the curve. And right now, for sure, I'll talk about shortcuts and things that I do, but there's just a lot of little gotcha rules. So honestly, the best thing you can do to figure out which side you're on is to just pick a point and test. Either the points below this curve are going to work, or the points above it would work. So my favorite testing point, uh, and it's related to the one that I like using even a linear situation, is the origin, because there's something so so clean about using x is 0, y is 0. So if I plug that in, this statement becomes, right, it becomes 0 is greater than 3, which is clearly false, right? This is not true. So that means that this point is not a solution. What that indicates is that, because I'm either on one side or the other, it indicates the other side is probably a solution. Now, off to the side here, I've placed a series of points that, if we were in class, probably without talking a lot, I would have had you just look at this inequality and tell me which ones of these are true. And then I probably would have you guys come up and as a group, place dots on a large XY graph in the room to just see which ones work. So if I was to give you, for example, this point, x is -1, y is 6. 1, 2, 3, 4, 5, 6. My hypothesis is that because this point lives above the curve, this should work, right? When x is -1 and y is 6. Well, if I plug that in, -2 times the -1 plus 3 is going to become 2 plus 3, which is going to be the number 5. And yeah, y was the number 6. So my statement becomes, if I'm looking at this equation, right? If I'm focusing on this equation, what I end up getting is, or inequality rather, I get 6 is greater than 5 when I plug in this point. Well, that's clearly true, right? So this point is legitimately a point on the graph. If I look at the point 2, 7, I believe this point will work as well. If I put in 2, I could just, what I could do is I could just make one set of this and just keep plugging it in. So it's always going to be -2 times, I'll place my x and then plus 3. And I'm going to compare that with the value of y, and y is the number 7 in this case. And maybe I should put a question mark here because I don't know if it's always true. But when I put x is 2 into here, this all of a sudden becomes -2 times 2, which is -4. -4 plus 3 is -1. And is it true that 7 is greater than 1? Yeah, that's true also. So this point is a solution. It's a graph a point that I would plot. Let's do a couple more here. So let's look at -1, 5. -1, 5 looks like it lives on the line, right? It looks like it's on the line. And because it's on the line, it's probably not a solution, right? Because the solutions, it says down here, y's have to be strictly greater than. So it's not going to include this endpoint. And when I put in the -1, I can see, oh, I get 2, right? Because -2 times 1, -1 is 2. 2 plus 3 is 5. 5 is greater than 5? No, 5 is not greater than 5. So I probably should come back in and say, you know what, this point actually is not a solution. Let me get rid of that point. And also I probably should come in and cross this one out because this point did not work. 5, 4 over 5 up 4. It's going to work. When I put a 5 in there, that's going to become, put a 5 in there, that's -10 plus 3. That's going to become -7. And on the other side of that, I got 4. Is 4 greater than -7? Yeah, that's why that dot's there. Let's look at 3, -1. That's going to work. 3 times -2 is -6. -6 plus 3 is -3. So I've got is -1 rather, greater than -3, and that's true. Boy, a lot of these work, huh? Must be cool. They're all working. What about 1, 6? 1, 6 is gonna work also. 0, 0. That's not gonna work. We already tried that one. We plugged that in. Oh, so why did you graph it? I didn't. And the last one is 4, -4. And 4, -4 is it's just right there. So it turns out that almost all the points I had in this list were solutions. And all the other points on the other side would not be solutions, right? All these other points on the other side would not work. So if I was to pick this point, for example, -6, 0, this point right here, and plug that in. If x is -6, this becomes the number 12. 12 plus 3 is the number 15. and I'm looking at y as 0, is 0 greater than 15? Clearly that's false. So this point is not a solution. So anything I would have picked that is below the curve, right? All these points below the curve would fail to make my inequality true, but all the points above the curve would satisfy it. And yes, it turns out when your inequality is written this way, right? It says, if you read this, it says, look, this is the boundary of the curve, right? Negative 2x plus 3 is the boundary of my curve. And I could read this as, hey, I want y values that are above the curve. I want y values that are greater than the curve. So if I pick any point and just go up from it, all of these y points that are above the curve would be solutions. And there are, you're right, there's an infinite number of them. That's why we never ask for an exhaustive list of them. Once we've got our boundary set, then we just say, you know what, it's just all of these. And we just kind of come in and just kind of gently, these are all solution points. So that's what we've got going on, right? We're going to be graphing inequalities. I want to look at one more example that may be a bit more challenging, and then I'll talk about some tools in Desmos. So let's go into our next example. Actually, before I get to the example, I want to look at three things that what I recommend as a solution technique for finding XY pairs that satisfy inequalities with two variables. I think a good idea is to first of all graph the boundary line, and we know how to do that. If you have an equation that is not in this form, right? You can easily transform the equation so it is in this form. The beauty of it is then you can easily see the slope parameter and the y-intercept parameter, and you can graph it. Anytime the inequality symbol is greater than or equal to, or if it's less than or equal to, that will be characterized by a solid boundary line. And we'll contrast that with if you've got strictly greater than or strictly less than, there we're going to have boundaries that are not solid. They'll be dashed boundary lines, just meaning that that boundary is not included. Points on that line are not solutions. Next thing we should do is test a point to determine which side is shaded. If this graph is not going through the origin, one of the easiest points you can test is 0, 0, right? So I recommend testing the origin if that's possible. And then if you test the origin and it makes the inequality true, that's the side that you should be shading on. If it makes it false, then you're going to be shading on the other side. So, and that's the last step then, is just shade that side that contains the XY pairs that make the inequality true. All right, let's move on now to our example. Okay, so let's look at 8x minus 2y is less than or equal to the number 10. So I'm going to begin by just considering the equality. So I'm going to look at 8x, pen. I'll look at 8x minus 2y is equal to 10. I am noticing that because this contains the less than or equal to symbol, that this boundary line points will be included. So I'm going to make this a solid boundary line, and I'll get y alone, isolate y by subtracting 8x from both sides. So negative 2y is equal to negative 8x plus 10. And then if I divide both sides by negative 2, I get that y is equal to 4x plus the number 5. So that's my boundary, and I can see that I've got a y-intercept at 5. And I have a slope pattern of up 4 over 1. And I'm going to go off the screen there. So I'm going to go down 4 and back 1, down 1, 2, 3, 4, and back 1. Down 1, 2, 3, 4, and back 1. 1, 2, 3, 4, and back 1. So these points should all be on that boundary line. And I just avoided a bit of heartache because as I'm sitting here looking at it, I'm just always constantly double checking, partly because I make goofy mistakes, but partly because it happens. It occurs to me that when I divided both sides by negative 2, I failed to divide this 10 by negative 2, right? I divided by positive 2. So what this should be is 4x and then minus 5, which changes things quite a bit. Same slope pattern, but now I'm living way down here with a y-intercept at negative 5. And then I am doing up 4, 1, 2, 3, 4 over 1. Up 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. And even now as I do that, I'm looking at this and like, did I get that right this time? And I'm literally plugging in those points that I'm looking at and just kind of testing that they actually work. And I think we're good this time. And if I take a ruler and draw it through those points, this is my boundary line. Again, it's solid because this was less than or equal to. Now, let's test a point. Let's test my favorite point, 0, 0. So I'm going to go ahead and take this point, and I'm going to plug it into the original inequality, right? So we've got x is 0 and y is 0. And if I plug that in, right, this is going to become 0 minus 2y. This will become 0. And then less than or equal to 10. So it turns out 0 is less than or equal to 10. That means that this point satisfies the inequality, and I'm going to be shading above the curve. Now, it's always nice to, you see me make mistakes often. So one of the things I might do is I might consider testing a point that's below the curve. Like if I tested the point, I could test the point x is 2. Let me put a question mark here. X is 2, y is negative 1. And if I give it the exact same treatment, for that point, we're going to be looking at x is 2, so we're going to have 8 times 2, or 16, minus, it's a minus 2 times negative 1, which is going to be plus 2, less than or equal to 10. 2 times 8 is 16. Negative 2 times negative 1 is positive 2. 16 plus 2 is 18. 18 is less than or equal to 10. That's clearly false, right? So this point that lives below my boundary is not one of my solutions. So I'm going to be thinking everything that is above this curve is a solution, including the curve. And I could just kind of artfully just sketch this region. So what we're looking at here is all xy pairs that are on that side. That's just terribly ugly. Are solutions. So a kind of nice view of some of these is the last inequality I did was 8x. So let's type this in here. 8x. And I do not want caps on. So 8x, and then minus 2y, and then we had that was well, equal to 10 was our boundary, and you can see that's that is the curve that we did graph. You can see we're going through here at negative 5, and we're going up 1, 2, 3, 4 over 1. So that looks correct. What we graphed was the simplified version. Well, we graphed it in y-intercept form. So we graphed y equals 4x minus 5. But it is kind of reassuring to see that, yeah, you can take this equation, solve it for y, and notice both of these equations have all the same xy pairs that are solutions, right? So that and this, right, are identical to each other. But then we were looking at the inequality. So the original inequality we had was it's less than or equal to 10. And you can see that it has shaded everything in above. Now I want to point this out because I'm good with shortcuts, and I'll talk about more in the coming days. But I want you to please notice that we're seeing the less than symbol in this problem, right? That doesn't mean if you see this symbol, you're always shading below the line. Because you may, let's face it, we're humans, we're pattern recognizers, and one of the things we do is like, hey, there's a pattern, I see this, and then we start doing that. I just want to caution you, there's a reason why that's happening, and it has to do with the coefficient of y. But for now, I think the best advice I can give you is to, A, find the boundary line, and then graph the boundary line. It'll either be solid or dashed. B, test a point like 0, 0 if it's available. That's my favorite point. If 0, 0 works, and it did here, you're shading above it. If it doesn't work, then you're shading below it. All right. So that's it. That's the story. That's it. Graphing uh, inequalities that have two variables, the x and y variables. This is Mr. Roberts. We're at 20 minutes. I hope you have a great day.